Hi everyone, my name is Mena. So today I'll be talking about building scalable APIs. I'll introduce myself in a bit. I have a slide dedicated to that, so that's why I'm not introducing myself just yet. Okay, 1 second. Yeah. Okay, so this will be the agenda for today. I'll be covering my introduction, what APIs are, understanding APIs, and scalability, architectural patterns for scalable APIs, key components for scalability, performance optimization techniques, deployment strategies for scalability, real-world case studies, and best practices and final tips. So about me. So I'm a software engineer. I've worked in a couple of places, Flutterwave, Stanbic IBTC, and I like cats. I like pets, and I particularly like cats and dogs. I like the golden retrievers and the tabby. I'm also a mentor. I enjoy mentoring women, and I am a huge advocate for women in tech. I enjoy learning. Um, just to highlight on the mentoring bit, I enjoy mentoring because you're able to give and also take back. It's not always a give-give situation. You're also able to learn from your mentee. I just enjoy learning. I try to learn as much stuff as possible every day. I enjoy traveling. I enjoy playing tennis. I started a new hobby, running, and I do enjoy it. And lastly, I like crime and thrilling movies. So yeah, that's it about me. So um, about API. Now to the topic of today, about APIs. So APIs are basically components that allow you communicate or allow software applications communicate. So they enable communication between different modern applications. So what does scalability mean in an API? So we've seen situations where the increase, and I'll talk about like some real world case studies about when an API when the load in an API, so for instance, more users, more data, more requests increase in an API or in an application rather, sometimes it tends to slow down the system. So scalability just talks about um, allowing that performance not affect. So allowing the increase of users or increase in load not affect the performance of your application. So why this matters, of course, like I mentioned, so that there's a consistent performance for every user, even as the load increases. Then there are various strategies to scalability. There's the vertical scaling, that is scaling up. So with this, we add more CPU power, like more powers like CPU, servers, RAMs, and so on. While horizontal scaling refers to, as the name describes, scaling out. So by adding more, I mentioned servers in the first one. I was wrong, sorry. I'm thinking I was a bit anxious now. So horizontal scaling basically refers to scaling out by adding more server instances and distributing the load amongst them. So this is typically used by a lot of large companies, and it allows for the dynamic addition of servers when there's an increase in load, and when there's a reduction in load, it also reduces the amount of servers that it scales to, or rather the API scales to. So um, vertical scaling is a good form of scaling strategy because it allows for simplicity, and then you can move on to horizontal scaling for long-term growth. So I just spoke here about like how horizontal scaling offers for better fault tolerance. If one node fails, there's another node that is available to pick up that request when an API request comes in. So I'm going to talk about the different architectural patterns for scalability. So we have the monolithic, which is the most common one. So here we have all your functionality deployed in a single code base. So this way is easy to develop, is easy to debug, but it's hard to scale. because when you want to make one change, you have to deploy the whole application, which is not ideal. So I'm going to talk about different architectures. So, speaking about the microservices architecture, we have each service deployed as a single, deployed individually and independently of each other. So, for instance, if we have an e-commerce website that has different APIs, so we can think of different APIs like orders API, payment API, the user authentication API. All these are deployed individually and independently of each other, and they can communicate through various networks protocol. So the pros of this over the monolithic, it's highly scalable. You're able to scale out and deallocate and allocate resources as demand increases or decreases. And one of the cons are it can be more complex in architecture. The next one is just showing the differences visually. So this is how a monolithic architecture would look and how a microservice architecture would look. We can see how the microservices are deployed independently of each other, and then they are communicating with the clients, which is the user interface. And while in the monolithic architecture, we can see everything is bundled up into one code base. So we have another architecture called event-driven. So event-driven architecture basically means that instead of the services communicating with each other, they can communicate through events. So basically, we can have, for instance, if we are to make, let me give an instance. So if we're to make a sorry, was that a question?
Oh no, sorry about that. I muted.
Okay. So when an event happens, so I was trying to use an instance. So when an event happens, like when a customer places an order through an e-commerce website, the order service order ORDER places an event into the queue. So we have different tools that can handle this, such as Kafka, RabbitMQ, and once it does this, the payment service listens for this event and then makes the payment, and then the inventory updates the stock of this event, and then the notification sends out to the client that, oh, this has happened. So in this case, it prevents the user from having to wait for all this process to complete. So it happens in the background while the user can perform whatever task the user wants to perform. So that's the event-driven architecture. So we have the asynchronous pattern. So in the asynchronous pattern, it's kind of similar to the event-driven. Here, tasks are handled without waiting for an immediate response time. So here it improves the efficiency. So instead of blocking a request until a task completes, it queues up this task and processes it in the background. So an instance could be YouTube or Instagram when we're trying to upload a picture or a video, and it immediately responds with upload successful while it's queuing for this video image to complete processing. So the video processing service picks up the task and starts uploading the video, and then we get a notification that, oh, okay, the user has been notified and they're allowed to watch this video now. The video is ready to watch on the application. So this is just the major difference, because I can see that it's a bit similar. So some of the key differences is in event-driven, it communicates through events. As opposed to asynchronous pattern. In event-driven, the services are loosely coupled, so they don't speak to each other directly, while in asynchronous pattern, there is room for inter-service communication. So some of the examples I gave here, like order system and a video uploading system, and then some of the differences in tools that they can use is in event-driven architecture, we can use Kafka, RabbitMQ, while in asynchronous pattern, we can use AWS SQS or Redis or Celery. Then the last one is stateless architecture. So basically, this one means that each request is independent of the next request. So basically, it doesn't save the session of um, a user's request. It makes horizontal scaling much more easier so that um, each as so that it can handle each request independently without having to remember the session. But if there's a need to have to remember the session, as opposed to saving it in a particular instance of an API that is deployed to the server, because when we save a session to an API that is to a server that has um, direct communication with a client, when this happens is there's there's a chance that that API instance can go down, and if that API instance goes down, we can't remember what was happening between that session with that client. So what we can do is we can store the session data in JWT or a shared data store. Then key components for scaling. So we have caching, load balancing, and database optimization. In the next few slides, I'm just going to go through all of them. So I'm just going to highlight them briefly. So caching just basically refers to saving frequently accessed data in your application, while load balancing is having a load balancer between your client and your API server. So what a load balancer does, there are different techniques that it does, but I'm going to describe one. So there's one that it checks for the least connection, the one that has the least connection, and then it routes your API request to that API server. So load balancing just basically makes sure that you are not deploying to one node, and when one node fails, you have an available API instance up and running. So we have database optimization. While we can deploy through caching and load balancing, there's database optimization that can allow that that can allow query optimization, sharding, read-write splitting, and connection pooling. So query optimization in this case could mean adding indexes to frequently access data in your database. I gave a brief example. I will share in the next few slides. Then sharding just refers to as splitting your data between shards. Then we have read-write splitting. It's very similar to sharding, but we have all read operations processed in a different database, while write operations are processed in a different database. So this is what I was explaining about database sharding. So they are basically split into the data is basically split into different shards, and they can be split by different properties. So it could be the user IDs or the regions. So for instance, if we have an application that we want to be available to different people in all parts of the world, or people in all parts of the world. So for instance, if I'm a user that I'm living in the United Kingdom, and the database that we have is deployed to, let's say, somewhere in Nigeria. Instead of me having to reach the database in Nigeria, we can deploy these shards in different parts of the region, in different parts of the world. So we can deploy this shard, for instance, in Europe. So it's faster for me to access that as opposed to me having to access one in Nigeria or in Africa. The latency will be really low. So yeah, then we have read-write splitting, just like I explained. Some of the use cases for read-write splitting could be for like read-heavy applications. Um, yeah. So this is an example of a load balancer. So as I was explaining, so different clients or different users are trying to access the API, and the API is deployed across different instances. This here represents a server, a server, a server. Our APIs are deployed into each of these servers, and each client is trying to access this. So instead of the client trying to access one API, they are deployed into several API instances, and it would allow us to not overload our APIs and make our application really slow as a client, to the client rather. Then next thing is database optimization. So this is just an example of us adding an index to frequently access data. So this just shows us trying to select select all from orders where the customer ID is 42. So if this is something we need to keep on frequently accessing, instead of trying to access it through normal SQL queries, we can do that through adding indexes. So this is an example of adding an index to our orders table for the customer ID column. Then performance optimization techniques. So there are various performance optimization techniques. I'm just going to quickly run through a few of them. So we have offloading time-consuming tasks to background workers. So this just simply talks about asynchronous processing. So like I mentioned in the earlier ones, instead of having to allow our users wait for an application, for a process to complete, we can offload them to background workers so as to reduce the reduce the load of what our APIs are doing, and they're able to respond quickly to other processes and other tasks. So minimize the payload. So a lot of us, I'm not sure if a lot of us, if we use REST APIs, but I use a lot of REST APIs, and I would like to think that a lot of us are familiar with this. So basically, what minimizing payloads is talking about is reducing the data sent over the network. So reducing the data sent over the network can improve the performance by reducing the latency of the response that is getting back to the HTTP. What am I saying? Reducing the responses that are getting back to the client. So we can consider different techniques like gzips on our API responses. Then we have pagination. So for endpoints that are returning lists, if we've noticed, like when we search on Google, Google returns a list of millions of records. Instead of returning the millions of records, we can return them in different chunks. So for instance, 50, 30, 40 as the need arises. And then the next thing is rate limiting. So rate limiting just refers to as controlling the number of requests so as to prevent abuse of the API. So controlling the number of requests on our API without trying to overload the API. Then we have CDNs. So CDNs just referred to as content delivery networks. So if we have an application that is serving us with static files or images that we know that will be consistent over a period of time, instead of requesting this from our APIs consistently or constantly, we can deploy them to constant delivery networks so that we can reduce the load on and allow our APIs perform more tasks that are not like, because it's almost redundant if it that we're only going to keep returning images and constant and static files basically. And then another performance optimization technique is profiling and monitoring. So basically what profiling means is analyzing the performance of your code. So it tracks the overall health performance of your API. And then monitoring just refers to as monitoring the resource usage of your application. So this helps to understand like what you can improve on in profiling. It helps you understand like what you can improve in your code. Maybe there are certain places in your code where you need to optimize for caching, while in monitoring, it helps you optimize like, oh, okay, if there's a certain spike in this, okay, we need to scale out our, for instance, if at 12 a.m. there's a huge spike in the orders API, we can scale out this API at this time so that it cannot impact the customer's experience on the application. Then talking about deployment strategies for scalability. So we have various deployment strategies. We have the microservices deployment. So just like the microservice architecture, basically what it does is allows you to deploy your APIs independently. So instead of one large monolithic application, we can deploy them separately as different instances, as different instances. That's it about the microservices. Then the serverless deployment. We've heard a lot about serverless deployments. So serverless means function as a service, and it eliminates the need for you to manually have to manage servers, just like the name says, serverless deployment. So instead, the API are deployed as functions, and they are triggered. And when they are triggered, that's when they run. So they are usually used for events, or like events that need to be triggered. So like notifications, emails, uploading images. That's when we can use serverless deployments. Then we have container orchestration. So containerization just allows our APIs to run in lightweight containers. So basically what it does is when we deploy our application, it deploys them in a container with all the dependencies. And we use orchestration tools like Kubernetes, Docker Swarm to manage these containers. So what it does is it monitors your application, and I gave an instance here, it monitors your application. So for instance, when the CPU usage of your application goes up, it deploys more instances so that it can scale out. And then like I said, like your customer's performance is also the performance on the user is also not impacted as well. And then if the demand drops, it removes these unused containers to save resources. Then we have the CI/CD pipelines. A lot of us are very familiar with this one. This is one of the most popular ones. So this allows us to push changes frequently and safely. So we can perform several functions with this, like automating API testing, deployments. It ensures for fast and reliable updates, and they can be rolled back. The next one is the hybrid approach. So this is just talking about like a combination of all the different strategies. I mean, there's no hard and fast rule to what strategy to use, but it's also advisable to, if you want, it's also advisable to measure and be careful about what strategy you're using, because all these strategies I've mentioned, they cost money. So it's important to know what strategy fits your purpose. So for instance, I gave an example here. A ride-sharing API would use microservices for modularity, Kubernetes for auto-scaling, CI/CD pipelines for frequent updates, and serverless functions for event-driven processing. So a real-world case study. So I use Netflix here as an example. In 2008, 2009, they faced a rapid increase in their demand. So they moved from their monolithic application to cloud-based microservices. And over the few years, they've decomposed this monolithic application to microservices. In 2012, they were able to complete the transition, and now they are able to scale. They've been able to scale their application and handle millions of requests every day. I think a lot of us can attest to the fact that a lot of us have used Netflix in one way or the other, and we can see that the impact, or we are not affected by the impact, despite the fact that millions of people are using Netflix every day at the minute. Yeah, so the final slide is just about the best practices and key takeaways. So always design for statelessness, always incorporate load balancing when you can, use rate limiting, monitoring and logging, and ensure versioning and compatibility. So basically what versioning means is if you have to make a change to your application, as opposed to deploying the change on if you have okay, so if you have existing customers and you have an application, if you want to deploy a change, you don't want to deploy a change that would be a breaking change and will set your customers back. You can deploy them using versioning. So for instance, version 1 of your API, version 2 of your API. So you can also roll back, then also incorporate testing, and importantly, documentation. Um, so lastly, I just wanted to highlight that scalability is a journey and not a destination. You can start out with building a monolithic application at first, and then understand at what scale you want to build your application to, and then try to fit in some of these deployment strategies and architectures that I have mentioned. And yeah, I think that's it.